Now I will to present you Professor Payam Barnaghi. It's a very, 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 very long background. He knows a lot of things, and and I hope that I am sure that it will be wonderful, amazing to hear him. Professor Payam Barnaghi shared in machine learning applied to medicine, Great Ormond Street Hospital, Royal Academy of Engineering researchers in machine intelligence for medicine. Wow. And deputy head of Division of Neurology in the Department of Brain Science at Imperial College of London. He's a principal investigator and group lead for translational machine intelligence in the Care Research and Technology Centre at the UK Dementia Research Institute, and a co-investigator and member of the steering committee at the British Heart Foundation Centre for Research Excellence at Imperial College. He's vice chair of the AEEC of Big Data Intelligent Networking and a visiting professor at the Great Ormond Street Institute of Child Health at University College of London. Payam Barnaghi is an NVIDIA Deep Learning Institute University ambassador. His main research goal is to develop a machine learning solutions for healthcare and create affordable and scalable digital system that can be applied across a range of health conditions. Please, Professor, do you have half an hour? A big applause for him.
Thank you, Manuel. First slide. Thank you, Manuel, for the kind introduction. That's the longest introductions I have had for a long time. And thank you, Raquel, for inviting me. And good afternoon. I don't know how you have seen this picture or not. When people talk about AI and the influence of AI and how it's going to change, I've seen this many times. People show this and say people who resist towards the influence of AI, like the teachers in 1960s who were resisting for calculators being in the school. Just to be clear, I sit with the camp that calculators should have no place in the school, just to know my biases. And also you hear a lot about the regulation, and this morning was a very, very interesting, great discussion about the regulations. A lot of tech companies, they come with this rhetoric of regulation will kill innovation or will stop innovation. I just wanted to highlight, at some point 500 years ago, there was somebody lived on this land who thought regulation will stop or limit their desire, and they decided to self-regulate. And history has not treated Henry VIII since then very well. Just point out, and if you see the still frame is from BBC drama about the Henry VIII. When I was preparing for this talk, as it happens, I started, let's say, ask the AI itself. Like one of the popular AIs, OpenAI's ChatGPT, asked, should I trust you? And I got this. I've just highlighted some points. So far, not too bad, actually. It says, no, you shouldn't. There are some limitations, and there are the issues. Actually, I like it's quite a fair response. Apart from the last sentence, which I've highlighted in yellow, says, well, it's up to you to decide whether you're going to use that. Now, that up to you is very subjective. There was a recent study published in BMJ showed like 1 in 5 GPs, they use ChatGPT. Now, put that next to, there was another study a few years ago at MIT. They created an AI and on purpose made the AI to make mistakes. And in fact, they did it in radiology. And then they sort of recruited 2 groups of highly professional clinicians, radiologists. They sort of divided them randomly to 2 groups. One group had the AI, other group didn't have the AI, and they gave them the same data set and asked them to make predictions. For the radiologists had the AI, they said, don't trust the AI, rely on your own intuition. It turns out, even if you tell, even the highly expert people, if you have the AI, radiologists which had the AI, they made more mistakes because the AI was designed to make mistakes. Then it's up to you. It can be very, very misleading because still, if you have a bad AI, it will make people make more mistakes. Now, if you look at how machines learn, most of you will know, but I've just oversimplified it. On the bottom left of the picture, I've shown like the statistical probabilistic machine learning, which has been around for decades. And usually the traditional or conventional machine learning methods was designed based on that. In that case, you know your data, you start engineering some features from your data, and then feed it to the model, and you learn. Those models usually requires less amount of data. They can do like better inference, like Bayesian models, and type of those are in that category. Over the past decade or so, deep learning, which I've shown on the bottom right of the picture, have taken a lot of sort of hype, and also there are very, very good applications coming out of it. And the notion is, if you have large amount of data, if you feed it to the model, and usually they are designed using deep neural networks, there's not only way of doing it, but usually there are deep neural networks at the moment. If you feed large volumes of data, you can train models which give you a very good inference sort of power. Now, the problem with that is also, like, if people get a little more beyond that, they say, oh, because we have lots of data, we can create global artificial intelligence. I'm not going to the philosophy of it. I just wanted to give an indication of what that will look like. If you have a phenomenon, which on the top row I've shown, like you have measuring two things. Let's say you have blood sample, you're measuring white and red blood cells. And imagine, for oversimplification, each of those values vary between 1 and 100. You will have 10 power 4, like 100 power 2 combination of the values you can get. And usually those models, if you have something like that, are linear models. You draw a line and separate it. Now, if you make it 3 sort of features with the same variation, you will have 10 power 6 or 100 power 3. And usually the model starts a little sort of becoming regularly, and usually you use like polynomial models or whatever you design that. Now, if you keep adding those features, for example, if you have 500 features, which I've shown in the 3 row, your decision space becomes now 10 power 1000, right? Or 100 power 500. Now, if you take that number, what a number is going to be 10 power 1000, and imagine each of those numbers, there was a tiny nanoscale grain of sand, just a tiny, the entire perceivable universe cannot accommodate that. Just to say, people who say if we have large amount of data with some autoregressive models, we can create models which can inference, is also highly dependent on it. Just a bunch of engineering methods is not going to solve. You will never have that amount of data to train the models. Now, generally how these models work, I've just taken an example of large language models, how they generally work. This is based on something we do at Great Ormond District Hospital, which I'll talk a little later about this. Imagine we have a patient. We want to sort of feed some patient's demographic or some of the giving patients demographics, which I've shown, I don't know, there's a laser pointer here, that's patient demographics. Given the patient demographics, I want to see what is the likelihood I would have had that sequence, for example, medication or procedures applied to that patient. This is a made-up data, sort of taken from real, but I've changed it for anonymization. Now, you can do it in multiple ways. This is a Bayesian way of doing it. Basically, you do a Bayesian inference, giving each of those conditions, you start creating conditional probabilities, and you start expanding it. The problem with Bayesian inference is when your space starts increasing, your probability calculating that will be a big integral. In computer science, we say that becomes intractable. It means you can never calculate that using like methods or writing the math behind it will be very, very complicated. Now, deep learning models, like large language models, they use sort of, they are statistical models. They use some complex sort of notion. They look at the patterns and they do some embeddings and they can create sort of this sequence. Then giving this patient demographic, I can see this sequence. But in reality, they generate it based on some statistical inference of that. This is a work my colleagues Iona and Ivan are doing. Iona is here today. And this is like, I'm showing an example. I work at the UK Dementia Research Institute. As part of my research, we are feeding a lot of publication from the institute, and we are trying to build a large language model. The application is not that important here for my example, but imagine, what did I do? Imagine we feed some text, and the model learns to represent, and then we ask questions. In this case, we have asked question, what is the relation between APOE? Is it genetic sort of mutations related to tau sort of pathology, which you will see in people living with dementia, and the model gives you some answer, right? And then we started this, we are using Llama, it's the Meta's Llama model. We started expanding it, like we asked the model first, like let's say generate 300 tokens, and then we started expanding it beyond the capacity of what our model could generate. And you see in the end, we say now generate 500 tokens. What happens, because this is probabilistic model, and you will sort of, you're calculating probability of each next token. What happens is how it works, it gives you a token, let's say relationship, and then calculates what's the next word is. And does that based on whatever I've seen before, and then becomes like as I showed, a large conditional sort of probability predicts the next one. Now, for each of the token, I've oversimplified it. Large language models use a temperature. They will sample from a possibility of the words they can give you. But generally, oversimplification, they will just predict what happens next. And you see, model gets to a point, suddenly everything becomes zero. Only plausible word becomes tau, tau, tau. And that's where start your modeling go wrong. Because if you're relying on statistical models, you get plausible things, but reality in your plausible thing relies on how the model inferences and what token is available and what probability comes out in that. Again, as I said, real like large language models will have a temperature, will sample, you just won't take the first one. They will do a sampling to get it. That's why you get the variation. And you can start seeing how now training this model, numerical precision and everything else, computational sort of limitations will start going wrong, right? And now some examples of things have gone wrong in the past, and I'll come back what we have learned and I've learned from doing this research. Oh, I've already spent half of my time. Okay, I need to speed off. And if I speak too fast, just tell me slow down. But one of the early examples of this was IBM Watson's IBM Watson. IBM created an application, played a quiz game, Jeopardy, and won. And then people say, oh, let's create this applications of it. And one of the very good examples of it was they created an application for oncology. It turns out they deployed it, and they got FDA approval, was used in some US hospitals, and then it started going wrong. And people started, what made it to go wrong? It turns out, actually, in IBM to train this, that they didn't use the real data. They used some hypothetical case scenarios they give to a group of doctors. They asked them to create scenarios, and they trained the model. And that was highly biased towards what that doctors thought. And amazingly, the regulatory pathway didn't pick that one up. Went and deployed, and the people started noticing, oh, wait a minute, this is not working right. And then it shows like how, again, training these models and transparency of these models, how they're trained, can indicate how they're going to perform in future. One of the more recent examples of it is EPIC's sepsis. Sepsis is a blood infection. A sort of infection gets into the blood system, and if you don't pick it up, it often happens to people in hospital, or could happen actually at home. It becomes very high risk, high risk of mortality. People in ICU, ITU usually constantly monitored for this, but still picking it up is always a challenging thing, and the early you pick this one up. EPIC is one of the biggest providers in the world of electronic healthcare records. EPIC recently, a couple of years ago, had an algorithm for detecting sepsis. They introduced it, and this was a paper published by a group of researchers, and they did a sort of a clinical study, and they concluded EPIC's sort of sepsis system works really well. And then they deployed it in fewer places, again, FDA approved and went, and then people started reporting, oh, wait a minute, it's not as good as it sounds like. At University of Michigan, they did an independent study because they were deploying it in one of their hospitals. And it's interesting, if you look at sensitivity and specificity here, you want your model to have higher sensitivity to pick it up. And if you look at the thresholds, like how these thresholds play together already shows you a problem. Where you're going to put your specificity, your sensitivity suddenly changes. Another thing that people started looking at is when you pick up the sepsis. Like if you're telling somebody in the moment of crisis, let's say if you're finding something, let me give you like Ellis here, you're saying somebody's going to have a kidney failure, 10 seconds before it happens, there is no clinical utility whatsoever. And a lot of machine learning models are trained based on a data at the point of that event happening. But the clinical utility is not there. And if you look at the sepsis, when actually sepsis became a crisis and people picked it up, there's no point. You need it to be somewhere here, like hours before to be able to predict it, or at least in a relevant time point of it. And it turns out one of the problems in early versions of this model was a group that trained the EPIC sepsis model. They gave the entire electronic healthcare record data for a patient who had sepsis in the hospital. It means I go to hospital, I stay for 10 days. I had sepsis in day 6. When they trained the model, they give my entire 10 days data, the entire clinical procedures. Obviously, I developed sepsis. Some events happened. You give some medication, and all that is fed already to the model. Your model is already biased because has seen events after the sepsis happened, and training this is completely pointless. And again, not working with clinicians and relying on computer scientists like me to develop it, I can develop something on paper that looks brilliant, but does not reflect anything about the main clinical practice. But that shows now 1460. Yeah, still I have. Ah, okay. I'm almost halfway through. Okay. Now, some of the things I've learned by doing it is that by no means is perfect. I'm not claiming, and some of the things as we do, I start learning. But I picked up some examples from work my colleagues and I have done to show what type of things go wrong or how you can remedy for that. One of the first things is knowing your data. Often, when people start developing machine learning, they will take a bunch of data and they will analyze it and they will show you some results. But in reality, investigating and understanding that data will have a huge value. One of the recent examples, at Great Ormond Street Hospital, the hospital has anonymized around 20 years of the entire electronic healthcare record data. That's around a billion electronic healthcare record data. We are working with developing some models to predict different outcomes. One of them we did was, can we give somebody's day one data and predict how long they're going to stay? We took 3 years of cardiology data, we trained, doesn't matter, a large language model here, technique doesn't matter. And then we measured it, how good our model is, we got good results. And then we started talking to our clinical colleagues. We said, look, we take whatever in the electronic healthcare record data written, like time stamp a day one or somebody, and we train it. It turns out, when we started talking, they said, oh, it doesn't work like that. The day, what you see is in somebody's day one, we go and update it in day two, day three, but we add it to their day one data. You have to look at the time of the date, this data stamped of the data entry, not what is associated to day one. Right? Because lots of this data is later on added, but added to somebody's day one. Now, somebody like me looking at data would have never, 100 years, I wouldn't have known that, I wouldn't have guessed that. But when you talk to people who do actual work, suddenly you get good insights. And that means our model, whatever it was, wouldn't have reflected the reality. We had training a model which has sort of had biases of the clinicians noticing other things in later on, and then adding them later, and we were assuming they were added in day one. We did a different work. My colleagues, Alex Capstick, created a model which we use in-home monitoring data and for monitoring urinary tract infections in people living with dementia. Now, this is one of the top 5 reasons people with dementia are at unplanned admissions into hospitals. And like anything else, we had a few hundreds of examples. We validated our sensitivity, specificity, and we showed it looks good. Nobody develops a UTI like this waking up and one day. Is a sort of a condition will start developing, bacteria will start building up in bladder, and then people will have symptoms, and we are picking some of those symptoms and we develop a model. But in reality, the very first versions, we have a few publications, don't read them, we were only focused here. Just once somebody had onset symptoms, and the symptoms were obvious, and we measured it against that. But in reality, the clinical utility is not there. And in a recent work we did, we went back and said, what if 1 day before, 2 days before, 3 days before, 4 days, 5 days before? And there you see, here you don't get the best sensitivity, specificity, or area under the curve. But I believe that's where your clinical utility is, because you start picking it up earlier. And if you pick up an infection earlier, you can do some different interventions to improve that. Another notion often gets unnoticed in data. If you have data coming from different sources, like if you have radiology images, or even we collect data from different homes, there will be quality differences, there will be distribution differences. And when we feed this to the machine models, we don't say where the data comes from, but in reality, the different quality of data can be misleading to machines. Then part of it also creating machines which are sort of an understanding of where the data comes from, and to be able to sort of accommodate those inconsistencies in the distributions of that data. Another thing is, when we develop these models, at least being an academic, I publish these things and I just get, and I move on to the next one. But often we don't notice what type of biases could have gone into this. Again, for a publication, I don't know, if you publish in Nature, they will ask you questions and you give the standard answer, we did X, Y, Z. But in reality, it's important to go back and reflect on how these models have been designed and worked. Again, in our UTI work, I showed you, and I said, oh, the results are good. Sensitivity, specificity was over 75%. Once we did this, while we were writing it up, we went and divided based on sex. It turns out our model was doing terribly bad for females. And now take urinary tract infections. Women age over 65, they have multifold higher risk of developing UTI. That means that model was doing terribly bad for women. Now, if I only reported this, you wouldn't have noticed this unless I break it down and I look at it. Now you can go across different demographics, those different socio-demographic features, and you see how your model performs. And sometimes these averages can be very, very misleading. In this case, it was a matter of calibration, and we could calibrate it. On the same note, Marzieh Ghassemian and her colleagues, they did a very, very interesting research. They were looking at, again, radiology images in the US, and they noticed at some point, African American in a certain region they were looking at had lesser data. Now, as a computer scientist, for me, when you have a biased data, bias is something I should get rid of because my models will work badly. I'll find up sampling, down sampling. You can do different things to do that. But in reality, that bias itself is data because there highlights some health inequality. Now, technically solving it is one issue. Highlighting an inequality you see in your data is another important thing. And they have written a very nice piece I think it was published in New England Journal of Medicine, of showing the sort of inequality. Sometimes also designing machine learning models, again, if you don't work with the people who do the field work, can be very, very misleading. I picked up this work. I'm not saying this is really interesting work. They are looking again for sepsis in relation to my previous discussion. And you see they have done some analysis. And they say one of the best features they pick is number of numerical measurements. Means you are measuring people's vital signs. And the number of the measurements in the model, it turns out to be one of the best predictors of somebody having sepsis. Sounds good. It's a good thing. There's no problem with that. Except you will start doing more measurements if you suspect I have sepsis. Means if I'm in an ICU unit, and you suspect I'm going to have ICU, sepsis, you start doing more measurements. In reality, the model doesn't do anything clever. It just picks up what clinicians had already noticed. Because I've been under higher observation, that means already the clinician was looking after me, noticed there's something might go wrong, and they started putting procedures, safeguards in place to collect more data. That more data being available for that patient which developed later on sepsis, it reflects the clinical sort of observation. If that somebody would have been missed in sort of a sepsis detection, your model also is going to miss. In reality, sometimes also what you see in data is important. It could be an artifact of the environment which collects that data, not in reality the model itself. Another notion I've learned by experience, again, this is something for a long time I was dismissed. I said, no, I won't do that. I just only do quantitative analysis. But in reality, qualitative analysis are also very important. This is a work my colleague Louise Rigney does at Great Ormond Street Hospital. Again, we are developing models, similar, I said, length of stay, looking at predicting complications, and also finding what we call a digital consultation. GOSH is a Center for Rare and Complex Disease. If somebody comes with a rare and complex disease, can you find similar patients to my current patient and see what happens to them and use that for a trajectory? Then we developed this model. We have this sort of large language model built from scratch, and we've we used the model. We find similar patients. We did our similarity of patients. We had some metrics to show how many events, ICD codes happened, and X, Y, Z to them. And we measured our model seems to be was okay. And then we gave it a subset of cases. We gave it to clinicians. I've just cut the letter we wrote to our clinical group. We had around 8 clinicians at GOSH. They volunteered to help us with this. And we gave them 50 cases and with similar patients we have found. And we asked them, do you find them useful? Unanimously, they said no. And at first, I was thinking, oh, maybe they are difficult. But we started asking them why. And then it turns out, what I see as a similar patient, I see it in a machine learning space. I see a patient as a vector, and I find another vector, and I say these two vectors seem to be similar. But for a clinician, similar patients have different meaning. Similar at what? The one of this was similar when they came to see me in the first place, similar to what happened to them, similar of the outcome, similar 2 days before outcome, similar in complications. And that suddenly changes your metrics. How you're going to train, how you're going to evaluate your models. And often these are the technical things when you focus, could be just misleading, just showing 98% accurate in finding all the ICD codes similar as shown in a patient similar can be highly misleading and not reflecting the real world. Another thing is a colleague of mine, I work with a colleague of mine, Christine Hine, she's an ethnographer, and she looks at the sort of ethics and also the real-world studies of these AI models. We had this AI model deployed in a dementia care scenario, and Christine went and talked to our patients and to people who were using this AI was deployed in their home, and also talked to clinicians. It was interesting. when I read the report, was completely different. Like what we were doing was completely different with what people thought we are doing to start with. We were doing in-home monitoring, and what people were thinking we monitor and we use it for was completely different than actually we were doing. And the clinicians' perception of what the ability of our model is was very different. Like they were thinking, for example, we can pick up any UTI. It's not true. I had reported them I can be only 75% accurate or whatever, but our clinicians assumed we don't need to worry about UTIs because there is an algorithm will pick it up. Then shows also the importance of understanding user perception. Now you can translate it to training, information, transparency. There are different ways you can do this. I just wanted to highlight the technical part of it. Another thing is to train any of these machine learning models, you need to collect data. The more you say you're doing precision medicine, personalized medicine, you're collecting more personalized data as we do. And then some of the technical methods to start with, data governance is important. I've given you some examples. Sometimes by just looking if your data is entirely anonymized, but just doing some inference, like looking at people, I don't know, for example, some variables, you can predict their alcohol consumption. You don't need them to declare how much alcohol they consume. You just need to look at some of the metabolic functions, some of the variables changing in their physiology and predict that. Then again, even if a data pseudo-anonymized or anonymized, it still needs to highly govern. Raquel tells me I have 5 minutes. I think I have only 2 slides. Another thing is the regulation of all these things. Like this morning, there was in the news with the incoming US government, FDA is going to significantly change. I'm not speculating in what direction it's going to change, but regulation of all these things affects individuals who now use or benefit from that AI. This is an example from a period application, monitoring application in the US. Lots of women have started not deleting it because the abortion laws in the US is changing. Now, certainty of who accesses that information, how that information is governed, it becomes a sort of a political issue, becomes a governance issue. I'm not going to go to the political landscape of that, but look at also 23andMe. If you have been following, this was a genetic testing and it's going bankrupt, and the whole argument is they might just sell your genetic data. Again, goes back, all this AI is good or generated or whatever. You need to also start fundamentally thinking, if you are collecting a lot of data for this and if you are sharing with some third parties to train these things, how this is going to be treated and used. Another thing is, being an academic, I write these papers and publish our results, and we say, let's say, if I tell you I have an algorithm works 80% accurate, probably I can manage to publish it somewhere. Nobody asked me, surprisingly, who are that 20% you fail? And we have started, recently we have this checklist. We don't publish anything unless we tick all this checklist. And one of the items in this checklist is, if you're X% accurate, just go and look at the patterns of those people we fail. If they're all female, if they're all certain age, if they are all living alone, that tells you something about the model itself. Often in reporting those models, even the regulators probably don't ask you that, but that gives you a very, very good indication of where you are failing, who you are failing. And now there are different ways, pathways of you can make it more ethical. My last slide on the technical subjects, there was a very good study it came out in Germany, it was published in Lancet Digital Health recently. They showed also the environmental effect of this. There is a hype of developing anything, a simple task. You want to do a regression, develop a large language model. And they showed like exponentially the carbon emission increases when you're using these models. Imagine if you're moving towards the NHS using AI and things, we need to think of what are the implications of running cost, environmental cost of all these things, and do we need that? Just to sum it up, designing any model, you have to first assume this is just always the AI gets the hype. I stand here and talk about the AI, and there's a huge array of other things needs to be in place in terms of the deployment, maintenance, feedback loops, and everything else came up during the discussion to make that work. And when you deploy, anticipate the risks, and then how you update that model, how you report it, which there was a good discussion around it. And who are going to benefit in getting engaged with them, and having this feedback loops. It's not just I design a model and I reported my UTI works 75%, I'm done. This is going to evolve over time, and each time you update it, you have to also be careful you're not introducing a new sort of problem or a new bias. Just to wrap it up, I'm always grateful for people with lived experience which help us to design, and every single dot I show in my slides is somebody's sort of experience in the challenging part of their life. I'm always grateful for that, and grateful to my colleagues who help us to do all this work. And thank you very much.
Thank you so much, Dr. Barnaghi, it has been impressive, fast but impressive. Thank you so much. For me, that the English is not my mother tongue, I will need to watch the video again to understand all the information. Impressive for me. We have 10 minutes to start some question and answers. Please.
Can I ask a question first?
Sure, please.
Good question.
So you mentioned like the model can learn some noise, like if the group is all boys or all girls. What if like we learn some noise from like if the data is collected in a sunny day or the data is collected in a rainy day? If situations like that, should we have criteria or should we have like some checklist for those when we're doing the machine learning or prediction modeling?
The question is, thank you, that's a very interesting one. The question is, I talked about the data coming from different sources. What if different time sort of stamps and data affected? Again, depends on application. For example, we have an application, we are looking at neuropsychiatric symptoms, agitation in people living with dementia, that's affected by time. In that sense, like time becomes a factor, and what time you have collected that data becomes a feature in your data. But if also some of these temporal dimensions could vary, or how you have measured time in different places. For example, we looked at training the model. Now, as a meta information, we tell the information. We are not using it to train the model, but we are letting model to see this information. Each time we give a sample to the model, we say where the data comes from. That comes from my house, from Raquel's house, and each time the model learns. Then we train the model to see, after like, let's say 10 epochs, which sources the model make more mistake. Let's say if in my house the data starts making more mistakes, the model, we said, don't learn less. This is not training the machine when not to learn. And we did this and it worked fine, because then you are limiting your, like if you're interested in machine learning, we are basically scaling your gradients. We are reducing the gradient effect and machine learns less. The problem is, once you do that, then we quickly figured out, oh, wait a minute, if I had a hospital and their data was noisier than a good hospital in London, I'm going to now discriminate against that hospital low resources because their data is noisier. My model performs better, but in reality, I'm discriminating for a subset of people. Then the technical solution we came up for that, or again, different ways of solving it, was we created now our models branch out. Means you have two different inference layers. When the model works up to a certain level equally to everyone, and then branches out. For the people who might be subject to the noise or whatever, we create a different inference, personalized, calibrated towards their data for other data sets. That's the solution we came up. I'm sure there will be better solutions in the future on that.
Thank you.
Okay. You have the micro, you have the power, but another question, please.
So when you're dealing with results that are using multiple data sources, I mean, it's nice that you're talking about feeding it, this is where this came from, this is where this came from. As someone involved with data provisioning for machine learning people, I've encountered the difficulty of knowing, well, how much did that data source contribute to your end result? Do you have some sort of techniques or advice for people where you're saying, look, we've done our thing, but now we'll tell you the breakdown of influence. That data set that's got these 10,000 records from that hospital really made a difference. These ones, for whatever reason, didn't. Do you have you developed any metrics or stuff like that?
That's a very, very good point. What we did, we were training some deep learning models, and we started monitoring gradients. Each time your machine makes an error per sample, you get an error feedback, and those like reflected in gradients. Then we started creating an array of gradients compared to the source. Then for each source per number of samples they had, we had a scale of, in this model, my gradients were an average higher than the other. And then in our case, first, at some point, we scale down now the learning model for the sources we make more noise, and we can report back on what sources we are making more noise, more mistakes, sorry. And then, obviously, to stop having been biased towards the good quality data and then ignoring the low quality data, we started branching out our model and recalibrating towards higher, noisier. Still, you will be less efficient, but at least you are not mixing it with high quality data and then eliminating their effect. Because if you learn less from the low noisy data, you will be less, you have a less predictive power on those. We want it also to be fair to those groups as well.
Questions?
Thank you very much.
Okay, a big applause. No.
Sorry, it's a bit dark and light is in our eyes, we can't see.
So on one solution I've seen to the kind of bias problems in data sets is people producing toolboxes of bias metrics or things that you can do, and effectively the kind of sell alongside those is if you do all of these things, then your data is unbiased. I find that quite a challenging concept, that you kind of tick enough boxes and then magically it's better. But the solution, kind of along the lines that you've got, is quite challenging in that it's thinking a lot more about your data. It's kind of being a lot more complex. How do you think we can encourage more people to adopt some of the approaches you're talking, rather than the box ticking approaches that are easier and require less thinking and less effort in many cases?
That's a brilliant point. It took me some time to learn this. I mean, I've been an academic for 20 years, and I think in the first 10 years of my career, I said I wrote the papers nobody read. And then I started thinking what we can do to make them useful. But one of the things we do in our lab, and is as a rule, we never stop designing machine learning model in the first place. We spend the first 6 months, what I say, we learn our data. We just do statistical tests. We look at how the features correlate. And often it's sort of also take hype area. Like it's easier I stand here and talk about large language model and show impressive graphs than saying I've done some statistical test and my features are how correlated and I understood like, oh, I have these biases. But also goes a bit about the, part of it needs the regulatory aspect and how we evaluate it and how we assess the work needs change. Part of it is the cultural change of, like a lot of people are interested in the endpoint of designing AI or machine learning because that seems to be the cool part, and less people are interested. I teach machine learning, and colleagues come to our lectures, I say like 80% or 90% of the AI, developing AI, is just doing the data cleaning and data curation. Is only 10% is the AI. Often people get the balance wrong. Thank you very much.
Thank you.